Welcome to the next video in the Mathematical Logic series on Chapter 2, First Order Logic, and in this video talking about the Homomorphism Theorem. First of all, let's talk about the canonical homomorphism. This is very familiar to abstract algebra. All of this stuff will be. So if you have a structure A and we form the quotient structure, the canonical homomorphism is a map from the full structure to the quotient structure, defined by mapping every element to its equivalence class. So, as somewhat promised, this is very similar to what we do in groups and rings, where, sometimes we call this the projection map or, something like that, where basically you just map an element to its equivalence class, and then you prove, right, sort of the point of that is that that is exactly the tool you want to prove certain isomorphism theorems and whatnot, and that is exactly what's coming around the corner. Before getting there, I guess sort of in development of exactly that idea, let's go ahead and state and almost kind of prove that the canonical homomorphism is a strong homomorphism. I'm not going to show much of the proof, but I'll just, do a first few steps and then indicate that the rest goes likewise. So take any constant symbol in our language. Now, what we want to do is we want to see that the image under the map K, which we're going to use to call the canonical homomorphism, is the same thing as that constant symbol's interpretation in the quotient structure, the range. Well, under this mapping, by definition of the map, the image is the equivalence class of C interpreted in A, but in fact that is just by construction of the quotient structure the same thing as the interpretation of C in the quotient structure. It's exactly what we wanted to prove. All of the rest of checking that this is a strong homomorphism is basically just like that. Okay, let's go ahead and state the homomorphism theorem. Now, part of what's in the book I've already done, that part which says that the canonical homomorphism is always a strong homomorphism, we've already seen. So I'm leaving that out of the statement here, and I'm just moving on to the part where we say A is some L structure, wavy equal sign is a congruence relation in A. Further, we assume that we have some surjective strong homomorphism from A to B, call it H, and we assume that the kernel of this homomorphism is wavy equal sign. Let's go ahead right now and recall what was the kernel, because we haven't talked about that in a minute. The definition of the kernel for a given homomorphism is an equivalence relation on A which holds if and only if some two elements have the same image. Moreover, we go ahead and define a map from the quotient structure to the structure B through the definition. Iota sends any equivalence class with representative A to the same thing that H sends A. So that's the definition of I, and the claim that we will make here is that I is an isomorphism, and also that H is actually the same thing as if you first pass through K and then pass through iota. So in the diagram, what that means, you imagine that we're starting with this strong surjective homomorphism from A to B. It's called H. We know already that by way of K, you can always go from the original structure down to the quotient structure, quotienting by the kernel of the map here, right? That's important. Not just any congruence relation, as there may be many, but specifically quotienting by the kernel of the map. When you do so, then this iota map, taking us straight from the quotient over to B, basically is a commutative diagram, right? That going straight over by H is actually the same thing as passing first through K and then through iota. That's the theorem that we're going to prove. I want to first show that iota, so defined, is well defined, because anytime your domain is a set of equivalence classes, you do have a legitimate worry about whether or not this is even a well-defined function. So let's assume that we have some two representations of the same equivalence class, that is to say the class of A equals the class of B, so these A and B are two different representatives of the same class, and we want to guarantee that iota of the class of A is actually equal to iota of the class of B, right? Since the iota was defined in terms of the representatives, this is a true concern, so let's make sure that we've got it right. We do, but let's prove it. By definition of iota, iota of the class of A just is h of A, and here's where the fact that the equivalence or the congruence relation that we're using is the kernel of H. Because that is the kernel of H, that guarantees that since the class of A equals the class of B, therefore H of A equals H of B. That's the important step. And then from there, everything else is immediate, right? Because, of course, H of B equals iota of the class of B, and then you chain those equalities together and we're done. In fact, the proof of injectivity, right? Because we want to prove that this is an isomorphism, so we want injectivity and surjectivity. The fact that iota is injective goes by a very similar proof, again, using the homomorphism. We can show that that by iota of the class of A equals the iota of the class of B, then we get that the class of A equals the class of B. So that would be injectivity. Surjectivity, I feel like, deserves a little bit of a note. Now, I stated the statement of the theorem with emphasis on the fact that H is surjective. In the book, that can kind of slip by you. It did for me for a little minute, because the book says that H is onto the range. Well, that means that H is surjective. And we need that in order to prove that iota is surjective. So the argument is, if you choose any element in the range, call it little b, then because H is surjective, then we know that some element in A, H of A is B, and then we can take its equivalence class and finish the proof. It's all right here. Very, very clear once you notice these facts. Okay. So because it's injective and surjective and a homomorphism, it therefore is an isomorphism. Oh, I guess I didn't check that it's a homomorphism, but I trust that that's probably very easy to check that iota is a homomorphism. Finally, we need to know this fact about the composition, and it's pretty easy, right? Because if we just write down iota compose K, that is evaluated on some element of A, then we first pass it into kappa. What does kappa do? It sends it to its equivalence class. Then what does iota of the equivalence class do? It sends it to the same thing that H does. Well, then that just means element by element, iota compose kappa and H each send the same things to the same things, so they are the same map.